Welcome everybody. This is going to be Calculus Section 2.1 with Graham Baez. That would be me. I'm going to narrate. We're going to have loads of fun. Yay for us. Okay. This section is rates of change and limits. Some of this is going to be kind of brief and I'm going to give you the overview kind of idea of everything in this section. And my phone went off. Okay. And then we'll move on from there. I would like to submit a formal warning to everybody that this lesson may lead some to die from boredom, and I highly recommend you go to sleep right now. Oh, and also I apologize for blurriness as cameras suck. So, without further ado, we're going to start with finding average speed. Okay, so we're going to start with finding average speed. We'll go with the equation y equals 16t squared between the times of t equals 0 and t equals 2. So our change in distance and our change in time, we're going to have, we're going to plug in the equation at 16 equals 2 squared minus 16, 0, 2, all of that over our change in time, which is going to be 2 minus 0. Okay, and then we do plug in the numbers, plug in the calculator, and we get the average speed is 32 feet per second. Okay, next we will be moving on to finding an instantaneous speed. So now we're going to find our instantaneous speed. We're going to use the same equation we did last time, but this time we have to use our favorite formula of f of x minus, no we don't. Yes we do, actually, I lied. I forgot the h. Okay, f of x plus h minus f of x all over h. Okay, so we're going to, first, we're going to plug in what we are, change in distance over change in time, because it's just like average speed. But this time, we're going to put in 2 plus h, the x squared, minus 16, just a 2, because it's a loner over there. All over h, of course, again. Now we're just going to start plugging in numbers. Actually, we're going to, my bad, we're going to square it. We're going to start simplifying, that's what I should have said. We're going to have 4 plus h squared minus 4h minus 16 times 4 over h. We're going to simplify that some more and get 64 plus 16h squared plus 64h minus 64. Then we're going to cross out the 64's here. 64 minus 64. Gotta remember to put over the h, take out the h, divide by h, there we go. Get rid of all them h's. And we have 16h plus 64. H, of course, equals 0, because we're going as the limit approaches 0, and that gets rid of their 16. And now we have that the instantaneous rate of speed at t equals 2 is 64 feet per second. Okay, so like I explained earlier, sorry for the crappy quality, and, well, yeah, the only way I really was able to do any of this. So instead I'm just going to read things to you, and that should work out fine. So, definition of limit. Assume f is defined in a neighborhood of c, and c and l be real numbers. The function f has a limit l as x approaches c. If given any positive number, weird Greek symbol, there is a positive number, different weird Greek symbol, such that for all x, 0 is greater than blah, blah, blah. Which basically means that the limit of f of x equals l as x approaches c. I'm going to read down there, limit of f of x as x approaches c equals l. Okay, we're going to do the properties of limits now. But instead of reading them all to you, which is going to suck, sorry, we're just going to have a little bit of dubstep music layover.
Yeah.
Okay, after that funness, we are going to move on to using properties of limits. If you missed any of the previous dubstepped over stuff, either go back and pause it, which you can do, or we have it in like all of our notes, so don't have to worry about it so much. But anyway, so we're going to move on now to using properties of limits. Well, just the sum and difference rule, actually, because I didn't want to do them all. Sorry. Okay, so now we are going to use properties sum and difference limit rule, as it were. Okay, so we're going to plug in the equation x third plus 4x squared minus 3 as a limit as x approaches c. Okay, so instead of a number, we're going to use c because we're all technical and whatnot. Okay, so as limit as x approaches c, x to the 3 plus, I'm going to write it again because, you know, why not? Equals the limit, so x approaches c, of running out of room, okay, x to the third plus, next line, okay, limit of x to the c for x squared. Basically, so what the sum and difference rule is letting us do here is space out. Instead of having the limit of one big equation, we are taking the limits of the different sections of the equation, making it a lot simpler. So now we are just going to plug in our c's for our x's, and we will get c cubed plus 4c squared minus 3. We're going to square that. We're good. Done. Okie dokie then. Now we're going to move on to the product rule. We're going to use the equation limit as x approaches 0, tangent of x over x, and we're going to have this little graph over here. And as you can see on the graph, it appears that the limits are going to be 1 if you graph that equation there. Okay, now we got our here product rule, which is tons of fun. Okay, so we're going to take the equation limit as x approaches 0, tangent x over x. My phone just went off. And we're going to split that apart. So it's going to equal limit of x approaches 0 of the sine of x over x times 1 over cosine of x, since we all know that tangent of x is sine x over cosine x. I forgot parenthesis. Okay. Equals the limit x approaches 0 sine of x over x times limit of x approaches 0 times 1 over cosine. Again, this is like the sum and difference rule, where it's allowing us to take what would be maybe a hard equation and spacing it out. And as you can see, again, from the graph above, it looks like the limit is 1, so we're going to plug in our 1 for our number there. And I actually lost what I did at this point, so ignore everything I'm writing down. But the answer is 1. End of story. Okay, aren't we having so much fun? I love this. Okay, sorry, sarcasm. Bazinga. Okay, so now we're going to do one-sided and two-sided limits, which is basically, you know, limits that have either the limit is the same point, or you have your broken up equation where the limits are different places, and that. Okay, so I'm going to read this for you guys. A function, f of x, has a limit as x approaches c if and only if the right hand and left hand limits at c exist and are equal. Also, we'll kind of along the same lines here. We're going to exploring a non-existent limit. As you can see from the equation here, is the limit x approaches 2, x cubed minus 1 over x minus 2. If we were to plug in that 2 there, it would not work because we would be dividing by 0, and math does not like us when we do that, so we can't do that. Which means that if we graph this thing, it's going to look something like this, or that. And I know that made no sense, but we're going to explore right and left hand limits here in a second. And basically what everything means is that when you have lines or equations or whatever, they have different limits as they approach from the positive or negative side, depending on, you know, what you get. I think pretty self-explanatory, but here we got a quick little thing right here, exploring right and left hand limits. Okay, time for an easy one. This is obviously this graph is, we all know what the, you know, sides are. So the limit as x approaches 3 from the negative side is going to be 2, I think. And x approaches 3 from the positive side, which would be the right hand side for us, is -1. Yay us. Okay, now we're on to making sandwiches, because we love sandwiches. I think Ms. J tried to explain this to us a little bit earlier in the year, and a lot of people were confused, and I am one of them, and so this is going to be fun. So sandwich theorem, if g of x is less than or equal to h of x for all x doesn't equal c in some interval about c, and limit of x approaches, I didn't put a letter there, g of x equals limit of x approaches c, h of x equals L, then limit of x as x approaches c equals L. Yeah, that would be why we were confused. Okay, so simplify. That just means that you take a crazy function. Here's my little messed up graph over there. You take a crazy function and you smash it between two other simple functions. In this case, it's x squared, x minus squared, and it makes it, you know, pretty. Because if you go where those two meet and what their limit is, then you can find what your crazy function's limit is. So now we're going to do, using the sandwich theorem, we have our little graph here. Just pretend that looks nice. It's a long stretch, I know, but pretend. And then here's our equation, is x squared sine of 1 over x. So x approaches 0, and we are smashing it between x squared and negative x squared to try and find out what its limit is. Okay, who's hungry? I'm not. Okay, since it's freaking 1 in the morning. Okay, sandwich theorem. Basically, you're taking a very complicated equation, and we're going to smash it between an equation we know better, like x squared. So the mumbo jumbo I'm writing down over here, is basically the technical way of saying, you know, this equation equals this equation times this equation smushed between this equation, as long as it sucks. So, honestly, my screwed up picture is the only thing you really need to look at over there. And yeah, so I'm going to pretend to narrate some more of this. It just took me so long to write it. Yeah, so we're smushing the sine of 1 over x. I think that's what that is a graph of, between x squared and negative x squared. That's what I'm writing right here. There we go. Okay, that makes a little bit more sense. And of course we're doing that as it approaches 0. Oh, and I need another piece of paper. Sorry. Okay, got it. And the answer to all of that is the limit is x approaches 0 is x squared minus sine whatever. Okay, anyways, yeah. Basically, sandwich theorem makes a sandwich. Call it good. Not being hungry anymore.
I'm a soul man. I'm a soul man. Let's see. I'm a soul man. I'm a soul man. Now grab a rope and I'll pull you in. Give you hope and be your only boyfriend. Yeah. Hey, Wanda. Wanda. What do you think now?
Focus?
Yeah.
Go ahead. I don't want to.
Okay. I'm a soul man.
Soul man,
I'm a soul man.
soul man.